So welcome everybody to this start of the new season of the official IAU G2 conference series. As usual, this is about massive stars, and today it's my real pleasure to introduce Sara Berlanas from the Centro de Astrobiología in Madrid. Hola, Sara.
Hi everybody.
Sara did her PhD thesis under the supervision of Artemio Herrero at the Instituto Astrofísica Canarias, finishing in 2019 and receiving for that the extraordinary PhD award from the Universidad de La Laguna in the Canary Islands. The title of her thesis was Massive Star in Cygnus OB2. During her predoctoral career, she spent a few months in Montpellier, working with Fabrice Martin and Kiel, collaborating with Nick Wright. And then in November 2019, she joined the team led by Ignacio Negueruela in Alicante as postdoctoral researcher. And later on in 2022, she was awarded an independent postdoctoral research grant to develop a project in collaboration with the universities of Alicante, Kiel, and La Laguna. And at present, she is working with Jesus Maiza Pellaniz at the Centre for Astrobiology in Madrid. Her main research interests focus on the spectroscopic analysis of massive OB-type stars in young cluster and associations, such as, for example, Cygnus and Carina in the Milky Way, as I'm sure she will be talking about. And she's also benefiting from the amazing data on parallaxes and proper motion delivered by the Gaia mission. She has participated in several international collaborations dealing with large spectroscopic surveys such as Gaia ESO and WIF-SIP surveys. And indeed, she's playing a key role in the building of the OB-star component of the WIF-SKIP survey, and also leading together with Artemio, a high-resolution survey benefiting from the high-resolution mode of WIF. And that's all from my side. I'm sure Sara will explain in more detail more things about her interests and future plans regarding this new generation of large spectroscopic surveys. Thank you very much once more, Sara, for accepting the invitation of the IAU G2 Commission. Whenever you want, the floor is yours.
Okay, thank you, Sergio. Hi, everybody, again. Today I want to talk a bit about young massive OB associations as laboratories for constraining the evolution of massive stars. So let me start by defining what an OB association is. It is true that there are several definitions of OB associations, but I would like to highlight the one given by Nick Wright et al. In 2023. OB associations are groups of young stars with a stellar density lower than that of the galactic field, and that are not strongly associated with the interstellar matter. As they stated, the density definition separates associations from open clusters, while the interstellar matter definition separates them from star-forming regions and embedded clusters. OB associations began to be explored in the 1950s, and since then, there are a long list of such associations that has been identified in our galaxy. This table from Nick Wright et al. In 2020 lists the most well-studied associations, such as, for example, Orion OB1, Vela OB2, or Cygnus OB2. The work also shows those that are clearly identified, but have not been yet extensively studied, such as other Cygnus OB associations, OB1, OB3, OB9, the Perseus OB2 association, or even Carina OB1. However, as you will see in a moment, there has been some effort on this last association since then. But there are other associations for which very little is known, including some that may not be a real association and still need to be confirmed, such as, for example, the Cassiopeia OB reader. As the membership of all these associations can be expanded and refined with improved photometry and spectroscopic, significant advances has been made in their study. For example, these studies include the first investigation of the 3D structure of OB associations and the identification of runaway OB stars ejected from the centers of these groups. I'm now going to focus on two of the most relevant young OB associations in the galaxy, Cygnus OB2 and Carina OB1. They are both relatively close to us. In fact, Cygnus OB2 is located at only 1.4 to 1.7 kiloparsecs from us and hosts more than 200 OB stars that can be analyzed in detail, despite of the high degree of extinction that we know that exists in that region. Carina OB1, which is visible from the southern hemisphere, is located at just 2.3 kiloparsecs and contains several star groups or clusters, including Trampler 14, which is the youngest cluster of the Milky Way with an estimated age of 1 megayear. Unfortunately, mainly because of the proximity, Gaia DR3 has provided us with accurate parallaxes and proper motions in both regions, allowing us to study also the dynamics in detail. In Cygnus OB2, my group and I have carried out several studies over the past decade. We first performed a membership study of the association and its surroundings in order to complete the known population of early data stars in the area. Using new spectroscopic observations, we increased the known OB population by 42 new OB stars, despite the existing limitation to completing the world census, as we know the extinction. We also investigated the age of the region, finding that the star formation has proceeded from lower to higher galactic longitudes, that is from Cygnus OB9 to Cygnus OB2. After that, we carried out a chemical analysis of a sample of OB stars to check for possible inhomogeneities and to test whether there is also a correlation between the chemical composition and galactic longitude that could evidence self-enrichment process. However, we found that the effect of self-enrichment by stellar winds and supernovae is too small to be detected within the accuracy of our analysis. So extending the sample and increasing the spectral quality is something required to reveal these effects. Then, thanks to the second Gaia data release, we studied in 2019 the spatial substructure of the association and found two stellar groups superposed in Cygnus OB2, but that are separated by around 400 parsecs. There is the main group at 1.7 kiloparsecs, and then a smaller foreground group at 1.4 kiloparsecs, more or less. In the fourth work, we presented the most complete spectroscopic census of our star carried out so far in Cygnus OB2, updating the binary fraction and performing quantitative spectroscopic analysis for the entire sample. From this, we derived the distribution of rotational velocities as well as physical and spectroscopic parameters, leading to two interesting results. First, we found an unexpected lack of very fast rotators that are present in other larger regions and are theoretically predicted, but I will back to that later. And we also found two main bursts of star formation at roughly 3 and 5 megayears. And finally, in our most recent work, we investigated a very luminous and highly obscure B1 supergiant that we had identified in the surroundings of Cygnus OB2 in our first study. It turns out to be one of the most luminous stars in the Milky Way. The star is in an advanced evolutionary stage, probably very close to becoming an early hypergiant. It shows a strong wind variability, and we found that it is orbiting another object. First estimates indicate a high probability that the companion was originally the primary stars, and it may even be a compact object, but we are currently working on a follow-up study. Regarding Carina OB1, we first used data from GES, GOES, and other literature sources to create the most complete census of massive stars in Carina today. The census contains a total of 316 massive stars, 18 in the background and 4 in the foreground. Within the CAROB1 association, we identify 74 O-type stars. In addition, the sample includes 20 spectroscopic binaries with an O-type primary and another 18 with a B-type primary. We evaluated the completeness of the census using a Gaia DR3 color magnitude diagram. On the left, we divided the census stars by spectral type and found that O and B stars can be clearly separated, so that confirms the accuracy of our spectral classification. And on the right, we included sources from Gaia DR3 that are consistent with the same distance to CAROB1. In blue, you can see those from our census. And looking at this diagram, we estimated that our census is about a 90% complete for low to moderate extinction, O and early B stars, meaning that we are likely missing very few or possible non-OB stars in CAROB1. In the second study, we carried out a quantitative spectroscopic analysis of the O-star sample in CAROB1 for which spectral data are available. Using high-resolution spectra from the GUESS and OWN surveys, we derived the distribution of rotational velocities for 38 O-stars in Carina. As in Cygnus OB2, and in contrast to studies in other regions and theoretical predictions, as I was said before, we found again a shorter tail of a rotator. This result requires deeper investigation, and in fact, we have already started working on it, as I will show you shortly. Finally, we also derived physical parameters using Gaia data and group distances. We constructed the HR diagram and found that the O-star population in CAROB1 is well constrained between 0 and 5 megayears. Using the bonsai tool, we derived individual ages for all analyzed members, obtaining an age distribution that peaks at 1 megayear. And this confirms CAROB1 and specifically Tramplin 14 as one of the youngest regions in the galaxy, as it was suggested by previous studies. Well, over the past decades, multiple spectroscopic surveys involving massive OB stars have been carried out, including Yakov, GOS, MONOS, GUESS, and more recently, the extragalactic Bloom and X2 surveys, among others. All these studies have provided a wealth of data, allowing us to study massive stars both in our galaxy and beyond. But the imminent arrival of two new multi-object spectroscopic instruments, WIP and FORMOST, is ideal for studying associations due to their combination of wide fields of view, typically several square degrees, and large numbers of fibers. This will allow us to observe hundreds or even thousands of stars at a time, spread over large areas, making them perfectly suited to the study of OB associations. Let me give you a quick overview of both instruments. WIP is the new Wi-Fi multi-object spectroscopic facility mounted on the Wilhelm Herschel telescope in La Palma since June 2022. In these two tables, you can see the main characteristics of WIP. It has 3 different observing modes, MOS, which allows simultaneous observation of almost 1,000 objects. Mini IFU, consisting on 20 mini integral field units with 37 fibers each. A LIFU mode, which is a single large IFU with more than 500 fibers. It also offers 2 possible spectral resolutions, 5,000 or 20,000, covering the wavelength range you can see in the second table. And just want to add that I just want to add that currently the LIFU mode is operational, while the MOS mode is about to enter its commissioning phase. WIP has 8 main surveys, and massive stars are included in the SKIP survey, which is divided into 3 components. It has a low resolution survey, which will cover all the northern galactic plane. And there are also 2 high resolution components focused on the anticenter and the Cygnus X star forming region. both covering a much smaller sky areas, but with many repeats. In addition to this, there are 4 MOS and 2 IFU science verification programs associated to SCIP. And we can say that the aim of the SCIP is to observe large stellar samples to study the young and old extremes of stellar evolution, along with the interstellar medium on a large scale. Focusing on the low resolution survey, it will cover around 1,200 square degrees of the northern galactic plane, including main OB associations. In this image, you can see the 410 field centers, each to observe once over the first 5-year period. And although the survey includes many different types of targets, the largest group is comprised of the more massive stars, types O, B, and A. But it is the Cygnus X SCIP survey, which will be fully focused on OB massive stars, and will obtain hundreds of multi-epoch OB spectra at the resolution of 20,000, covering the main OB associations in this complex. We want to secure high signal-to-noise spectra and the highest possible resolution to firstly obtain accurate abundances to check possible chemical patterns, obtain rotational velocities and their distribution, thus improving previous works that we started in Cygnus OB2, determine binary fractions thanks to multi-epoch observations. Again, although there is a much smaller number of fields, it will be many repeats. We will be also able to detect peculiar objects like NB, hypergiant, extreme supergiants, or possible gravitational waves progenitors. And of course, determine accurate spectroscopic parameters, improving those from the low resolution, but also obtain luminosities, masses, and radii thanks to Gaia. And finally, we will also be able to explore the kinematical and dynamical status of the stars in that region. Well, our selection criteria are based on a combination of 2MASS, Gaia, and IGATS data. We basically score the targets depending on their location in the color, and color magnitude diagrams. And after adding up all the scores, those objects with the highest score will represent our most reliable candidates. Here you can see the footprint where the selected OB candidates to be observed are indicated with yellow points. Circles are the pointings or field centers. And although there are only 7, 3 of them containing the cores of Cygnus OB2, OB9, and OB1 are repeated to allow a better coverage of these crowded regions. But OB stars are not the only targets. We have also included B, A, F, pre-main sequence and YSO stars, spades, white dwarfs, and red supergiants. Apart from this survey, one of the SCIP SV programs is focused on OB stars with 1 low resolution and 2 high resolution pointings. We chose the same field center for the 3 observations in the Cygnus OB2 or the rosette, depending on the visibility. With this SV program, we will be able to validate our selection criteria of OB stars, to test the saturation limits, to compare low resolution and high resolution spectra for the same sources, because we ensured that at least 30% of the stars are in common between these 3 configurations. And, for example, to prepare analysis tools for the science exploitation. If Cygnus OB2 is observed, we will obtain an improved distribution of rotational velocities to check the unexpected lack of fast rotators found in previous studies. And if the Rosette Nebula is observed, then we will be able to create the HR diagram for the complete OB stars plus the YSO population, as we share SV pointings in this region. On the other hand, for MOS can be considered as the width complement in the southern hemisphere. Here you can see its main characteristics. It also offers 2 different resolution modes and allows to simultaneously observe up to 2,400 objects. One of its surveys is formidable, whose main objective is to produce comprehensive chemokinematical maps, which will be used to, for example, expand the legacy of Gaia with complementary radial velocity and chemical information. And thanks to the collaboration of Sergio Simón Díaz and Norberto Castro, this survey includes thousands of OB candidates whose footprint you can see here, and that will cover, for example, the Carina Nebula. So we'll complement guest data and ongoing studies on OB association in that area and beyond. And finally, I want to broadly present the MAGAS project, although those who attended last week's symposium on massive stars will be hearing it again. Sorry for this, but I'm going to compress the info. Well, MAGAS aims to carry out comprehensive studies in the major star forming regions and OB associations by using data from Gaia releases, with and foremost, and other existing surveys on massive stars. In addition, multi-wavelength counterparts will be secured through open time observing proposals when necessary. In this way, we will compile the necessary information to adequately characterize these regions, providing the most robust empirical constraint on stellar parameters, as well as the consistency that is required to improve our still poorly known evolutionary pathways of massive stars. As a first phase, MAGAS will focus on establishing the universality of the rotational distribution of massive OB stars. We all know that given that massive stars are usually born in multiple systems, where the components are close enough to interact during their lifetime, the possible channels of evolution of final fate are multiplied, and their impact depends on their frequency. Our hypothesis is that these frequencies are written in the rotational distribution and in the stellar properties and abundances. And although the census of possible evolutionary scenarios is not yet complete, we aim for a first empirical estimation. The vicinal distribution of massive stars can be used as an evidence for the evolutionary behavior. For example, fast-rotating massive stars have been proposed as products of interaction processes. Here you can see the well-known vicinal distribution from the Mink et al. 2013, indicating the possible evolutionary scenarios as well as the expected frequency of post-binary interactions. And also, massive runaway stars can be the product of post-interacting binaries ejected at high velocities, as shown in works by Sana et al. 2022 and Britabsky et al. 2023. Then the first phase of MAGAS is focused on determining for the first time ever whether the empirical vicinal distribution of massive OB stars is universal, as theory predicts, or not, as findings in Cygnus OB2 and CAR OB1 suggest. I remarked that establishing the universality or not of the rotational distribution for massive OB stars is crucial for comparing the frequencies in different environments. So if the distribution is confirmed as an universal function, then the possible evolutionary scenarios will occur with the same frequency in any environment we consider. But if significant differences are confirmed, we must explore whether these frequencies are intrinsically different, are intrinsically the same, but they occur at different time scales, or they are intrinsically the same, but depend on the environment properties, like, for example, the age, density, or etc. So to this end, it is mandatory to first verify whether the significant differences we have found in Cygnus OB2 and CAR OB1 arise from specific environmental properties associated to young OB associations. Completeness on the stellar census is something crucial for these studies, so infrared observations are needed to uncover the obscure young population that is still embedded in their birth cocoon. We have started infrared studies in both regions. We are inspecting the obscure population in Chamber 14 using KMOS at the VLP. And an infrared spectroscopic study in Cygnus OB2 will be done with a mirror at the GTC using IAC guaranteed time, thanks to the collaboration of Artemio Herrero in this project. Secondly, and as I said before, it is known that massive runaway stars can be signatures of binary interactions that have been ejected at high velocity from the core of the stellar association. Then the missed sample of fast-rotating stars in Cygnus OB2 and OB1 might be the product of post-interactive binaries ejected from their core. In such a case, we would recover the predicted distribution function, and the frequencies of the possible evolutionary paths could be assumed as intrinsically the same, but affected by the environment conditions. We have started a study using the OSIRIS and Megara instrument at the GTC to identify OB runaway candidates in the surroundings of Cygnus OB2, and whose data are right now under analysis and appear to be very promising at the moment. We also must check whether the lack of fast rotators is also present in other young OB associations. So we will use WIF and HORMOS data to extend research to both Cygnus and Carina complexes, but also to other galactic massive associations, such as NGC 6611, Westerland 1 and 2, or even the Vela, Orion, and Monoceros regions. And of course, we will also make use of already available spectra from other surveys. And finally, we will also inspect both the LMC and SMC in order to add in two further environments that will serve to address a possible metallicity effect on the universality of the distribution. To this end, we can make use of data and results from BFPS, X2 and Bloom. And here you can see preliminary results from Bloom in the SMC that will be published very soon, where we find fast rotating or single or apparently single stars above 400 kilometers per second, in agreement again with theoretical predictions. So to sum up, just want to say that the arrival of large spectroscopic surveys will lead to an important improvement of our knowledge of star formation and evolution of star-forming regions and clusters, including our understanding of the dynamical and kinematics of OB associations and stellar groups. And that's all from me. And thank you very much for your attention.
Thank you very much, Sara. It's amazing the amount of data that soon we'll have in our hands, and very interesting results you have presented. Now it's time for questions. So please, if anyone wants to ask any question to Sara. Miriam?
Hello.
Hi, Miriam.
Hi, Sara. So determining what's the role of environment is one of the crucial point of your plans. I was wondering if you plan to do something related to ISM, and I don't know, maybe this sounds crazy, but studying whether the ISM is more turbulent around one OB association or another, also chemical composition, dynamics, things like that.
Well, that's a good point and a good idea, but well, I think it's something that we can consider, but for a future outlook. I mean, what I want to do right now is to take advantage of all the data we already have, or the incoming data that we have, and use this optical and infrared data, but within the association, the surroundings also. But well, it's a good point that yes, I will consider and talk with you.
Yeah, I was
Yeah.
thinking about this because I heard you have Megara observations.
Yeah.
So I was wondering if it's the IFU or the positioners, and because I thought the positioners were not working yet. So I was a bit envious.
Sorry again.
Yeah, you said you have
Yeah.
Megara
Megara
observations of
for
Signal.
some runaway candidates in the surroundings of Cygnus OB2.
So is it with the IFU or with the?
Yes, IFU.
Okay. Yeah. So then you have the information on the gas. Well, Norberto knows a lot more than myself about this.
Okay, so we can take advantage of this data.
Yeah.
You think? Yeah. Okay. Great.
So if there are no other questions, I wanted to ask another thing.
Please.
So you gave us a preview of the results with the Bloom.
Yeah.
I was wondering, aren't you losing information? Because now you have your different clusters and you know the age. But if you compare to the whole SMC, I think it's all
that's true. This is like when we compare with the whole Milky Way or 30 Dorados, not focusing on specific clusters, I mean. So yes, the data from the SMC is like field the stars for SETI. And well, I think that it could serve to look for possible metallicity effect, comparing, for example, with the Milky Way or the LMC. But yes, Bloom is not only focused on the specific jump clusters. So
yeah, I don't know the population studied by Bloom, but maybe you could take a step back and disentangle ages, perhaps. Well, thank you.
Thank you to you.
Yo.
Oh, Sara, very nice talk. Thanks a lot. So I'm asking a question. Maybe you have answered it during the last 10 minutes, but I had to vanish for 10 minutes. So nevertheless, have you any promising hypothesis for the missing fast rotating objects?
Well, I really think that it could be due to a mix of things, mainly runaway stars, that that there's a connection or between the fast rotation and runaways. So maybe I think that most of or many of the runaway stars that has been ejected from the core of this association can be the fast rotators that we don't find in the distribution. But because the studies are focused in the cores, not in the surroundings.
Okay.
So this is why we are looking in the surroundings, in a ring around the cores, to look for the runaway population of OB stars to measure their vicinity distribution. Of course, it could be also due to possible obscure population that we haven't found in this association. So we are also looking for the obscure population in the associations, but I think that could be a mix of things. Also, maybe the density of these regions are involved on the binary interactions, and maybe, I don't know. I think we want to start exploring mainly these runaways and obscure population, and look what is happening. Something we found to improve our vision of the distribution. But I have the impression that could be a mix of things.
Okay, thanks a lot.
Thank you.
Jaime?
Hi, Sara. Thank you for your nice talk.
Thank
So
you.
this is a follow-up question from Joe's question. Have you seen or have you checked the number of emission line objects, or the fraction of emission line objects in comparison to other regions? Like
no, but because we don't have a large sample, an homogeneous samples. And this is why I think that with for both associations will be very, very important for us, because we will have a large sample of OV stars, and probably many of them with emission lines, emission OV stars, to check other possibilities.
I see. Thank you.
So now it's my turn, because it's a follow-up of Jaime's question.
Okay.
Since already Joe asked something I wanted to ask. Obviously, you are going to benefit from many mid and high resolution surveys.
Yeah.
That is important for determining the stellar parameters. But what about, and this is something I learned while preparing the overview talk for the IAU symposium, what about these other surveys that are low resolution, using Sloan or the Sloan survey, and also LAMUS? So I know, and maybe Jaime can also explain a bit, but I know they are being very efficient to confirm OV star candidates and doing some preliminary parameter determination. But how you think you can benefit from these surveys that are below 2000 resolution? This is my first question, and in a related question, what about Gaia? Have you thought about what would be the utility of the Gaia RVS data for you? Is something to take into account to complement, or?
Well, the problem of Gaia, the RV, and the high resolution spectra is the wavelength range, that it is not very useful for, at the moment, at least, for the analysis of massive stars. Your question about using low resolution spectra or surveys, well, I think that it would be very useful for at least identify OV stars, like a first good, and also to identify the very fast rotators. Because we will see, of course, the rotational velocities are affected by the resolution of the spectra, but for very fast rotators, we will see that this is a very fast rotator. So I think it is useful, in fact, could be very useful to a first code, and then try to apply for high resolution observations to make a proper analysis of the spectra, derive accurate rotational parameters and abundances and everything. But yes, I think they will be very, very useful. It's like GOES. I have used GOES for a lot of things.
Okay, thank you. Artemio? We cannot hear you if you're trying to talk.
Yeah, now?
Yes.
Yes.
Yeah, excuse me. Yeah, I was saying thanks, Sara, for the very nice talk. And I'm sorry that my case is just the opposite to Joe. I arrived 10 or 15 minutes late. And I don't know whether you mentioned it, but just to complement your answer to Joe's question, Sara and her student, Daniel Galan, have a very advanced draft about the Cygnus OV2 V-sinusoid distribution, including a long discussion about the possible reasons why we observe this lack of Cygnus OV2. We will send you a draft as soon as this is in a practically finished stage. Thanks.
Thank you, Artemio.
Any more questions? Well, if not, in any case, I'm sure Sara will answer you any question you have. You just send her a mail. So thank you very much, Sara, for this very nice overview of OV stars in clusters and associations. And thank you, everybody, for joining. So stay tuned for the next talks. We will continue directly until June. Thank you very much, everybody.
Okay, thank you. Bye, guys.
Ciao, ciao.
Bye.